7.3, partial fraction decomposition. A rational expression can often be written as the sum of two or more simpler rational expressions. For example, x plus 7 over x squared minus x minus 6 can be written as the sum of two fractions with linear denominators. We can write this as 2 over x minus 3 plus negative 1 over x plus 2. And if you aren't sure about that, we could get a common denominator and figure this out. So we could multiply this by x plus 2. And we could multiply the other by x minus 3. Well, let's see what we get. So that's going to give us, let's see, in the denominator we'll have x minus 3 times x plus 2. That is going to give us x squared minus x minus 6. So actually we can probably combine these guys here. And up top, when I distribute this, that's going to give me 2x plus 4. And then I have distributing the negative 1, that's negative x plus 3. And when I clean that up, this is going to give me x. These are going to give me 7 over x squared minus x minus 6. And there you have it. They are equivalent. So each fraction on the right side of this equation is called a partial fraction. Together, they make up the partial fraction decomposition. And decomposition just means to break apart or to break down. Okay, so we can decompose our rational functions really in a few different ways. So we can divide if it is improper. So if the fraction is an improper fraction, meaning that the degree up top is bigger or equal than the degree below, say I have like x squared on top but just x in the bottom, then you're going to divide the denominator into the numerator to get the polynomial plus numerator over denominator here. Okay, and we're going to see some examples like this. If we can factor the denominator, we absolutely are going to do this. So if we can factor the denominator, we are going to factor it. It's going to make our lives a lot easier. For linear factors, for each of these factors of the form px plus q to the m power, the partial fraction decomposition must include the following sum of m fractions. So whatever this exponent is, that's how many fractions you're going to have. And then for quadratic factors, for each factor of the form ax squared plus bx plus c to the n power, the partial fraction decomposition must include the sum of n fractions, and they're going to be of this form. So instead with linear, where we just have a1, a2, and so on up top, here I'm going to have b1x plus c, so I'm going to have linear on top where I had constants on top before. One of the most important applications of partial fractions is going to be in calculus. Partial fractions can be used in calculus for the operation called antidifferentiation, though it has a couple other names. So first, let's try to write the partial fraction decomposition of x plus 7 over x squared minus x minus 6. We already know the answer, but let's go through that process. So, first of all, this expression is considered proper. It's a proper fraction because the numerator is a lower degree than the denominator. So I don't have to worry about any crazy division here. Okay, so right away what I can say is I'm going to factor. I don't have to worry about step 1. I'm going to factor. So let's factor that denominator. So we have x plus 7. And if I factor this denominator, we're going to have... well, actually, we can leave that for now. Let's just factor. So we have x squared minus x minus 6, and that is going to factor into an x and an x. And you want to say what things multiply to 6, technically negative 6, and are going to give me that negative 1 in the middle. So that's going to be a minus 3 and a plus 2. So I'm going to take this, and this fraction can be written as two fractions added together. We'll use one of these in the bottom for one fraction and one of these in the other. Now I'm just going to call these A and B for now because I don't know what belongs there. All right, so what we're going to do now is to multiply A and B as if we were getting common factors. So let's actually get this all on one line also. So we have x plus 7 over x squared minus x minus 6 is equal to that sum. All right, so if I had wanted to add those two together, what I would have done is multiply this by x plus 2 and this by x plus 2. And over here, I would multiply this by x minus 3 and x minus 3. Okay. But what I could actually do, if you remember from Algebra 2, is save myself a little bit of time. And instead of just getting these to have a common denominator, I can actually multiply to remove the denominator entirely. So what I can do is multiply both sides of my equation by a common factor. So that common factor is going to be x minus 3 times x plus 2. And I can multiply both sides by this, x minus 3 times x plus 2. The beauty of doing that is it's going to cancel out the denominator on the left-hand side. I'll get left with x plus 7. Over on the right, I'm going to distribute when I multiply that. So when I multiply to the first fraction, the x minus 3 will cancel. That'll give me a times x plus 2. When I multiply the second fraction, the x plus 2 will cancel. That's going to leave me b times x minus 3. All right, so now we can clean this up. Let's distribute the a and distribute the b. So we have x plus 7 is equal to ax plus 2a plus bx minus 3b. Okay. And what we want to do here is to now try to make this more in a polynomial form where we put the x's together. So I'm going to put these two next to each other first. And then I want to make sure I factor so that I just have an x. So I'm going to factor that x out. That's going to leave me with a plus b times x plus, and then 2a minus 3b is really just a constant. All right, so now what I want to do, because these two polynomials are going to be equal if and only if the coefficients of like terms are equal. So this is of the form a number x plus a number. All right, well, a number x plus a number. So these two are only going to be equal if this number equals this one and this number equals this one. So what we're going to do here is set up a system of equations. All right, so I'm going to have that a plus b equals 1. And I have 2a minus 3b is equal to 7. And now I can solve, and you can solve this any of the different ways, though I don't know that a matrix is our best choice. I mean, it is an option. I would like to do this by elimination, though. So we'll multiply that top row, let's say by 3. So that's 3a plus 3b is equal to 3. The bottom row can stay the same. And when we add these together, that's going to give us 5a equals 10, or that a equals 2. And then we can plug back in to get b. So a plus b is equal to 1. That means 2 plus b equals 1. Subtract and get b is negative 1. So my final answer is going to be, I'll go right back up here and replace a and b. That's going to be 2 over x minus 3 plus negative 1 over x plus 2, or you could write that as minus 1 over x plus 2, and it would really be the same answer. All right, let's take a look at the next one. So the next example shows how to find the partial fraction decomposition for a rational function whose denominator has a repeated factor. So here again, I notice the numerator is going to be a smaller degree, so I don't have to worry about the crazy division stuff. But what I do want to do is factor the denominator. Okay, so I have x cubed plus 2x squared plus x. We have a GCF of x. That's x squared plus 2x plus 1. And then when I go to factor that, it's going to give us x plus 1 squared. So x times x plus 1 squared. All right, so when I go to factor this, this is what's going to happen. This gets a little bit funny, and it's only because of that squared, having that little 2 on that factor. So I'm going to have something over x, I'm going to have something over x plus 1, but what I'm also going to have is something over x plus 1 squared. So had this been cubed, I would have done x plus 1 squared, x plus 1 cubed. So every time I'm just going to do one for each and start to count up. All right, so this time I need a, b, and c. Okay. So again, we want to multiply to get rid of the fraction. So we're going to multiply by x times x plus 1 squared on both sides. That's going to cancel the denominator on the left. That'll leave me with 5x squared plus 20x plus 6. On the right, what's going to happen is the x cancels. That's going to give me a times x plus 1 squared. Plus the x plus 1 is going to cancel. One of them will. So that's going to leave me with b times x plus 1. And then for c, what's going to happen is that x plus 1 squared will cancel. So that's going to leave me with cx. All right, so on the right, I need to do a little bit of cleanup here. I do want to FOIL that out as well. So we have 5x squared plus 20x plus 6 is equal to, that's a times, that's x squared plus 2x plus 1. This is going to give me bx squared plus bx and then plus cx. I still need to distribute my a. So that's ax squared plus 2ax plus a plus bx squared plus bx plus cx. Okay. So the next thing I want to do is group my x's, my x squareds, and my constants. So I have ax squared and bx squared, so that's a plus bx squared. Plus, I want to group all my x's. So that's 2a plus b plus c x plus, and then my constant a. Okay. So the next thing I want to do is, using the same logic, something times x squared plus something times x plus something. So those somethings have to be the same. So I really have a system again here. So I have that a plus b is equal to 5. I have that 2a plus b plus c is equal to 20. And I have that a is equal to 6. Well, that's convenient that we actually know a. We can use that to plug in right here. So that's going to give me that 6 plus b is 5. So that means that b equals -1. And then I can use this equation, 2 times 6 plus -1 plus c is 20. That's 12 minus 1 plus c. 11 plus c is 20. That means that c is going to give us 9. Okay. So now what we can do is rewrite this. We're going to go back up here and just replace a, b, and c. So that's going to give us, let's see, a was 6. So 6 over x plus b was -1. So if you want to write minus, we could do that. -1 over x plus 1. And c was 9 over x plus 1.